And again, let me just talk about the test. So again, the base time for the test is next Monday at 3:30. Because I'm going to just give you the 2-hour time, it will start at 3:30 as opposed to the usual for the other two tests, the 5 minutes or whatever before it, because you already have a little extra time, so I'm not going to worry about that as much. But so it'll start at 3:30. You have until 5:30. That way, if there's a little trouble at the beginning, it's still okay. Well, it's not a final, so it's just a third test, and it is just mine. I'll talk about what's on it in a second. Yeah, so there are 3 sections. We all have at least slightly different tests. So for example, the other 2 people had already tested 3.11, so they don't have 3.11 on their test 3. So again, if you're taking it tomorrow, which is basically the one time tomorrow is 1 p.m., I probably have emailed you already, although if someone emailed me later this morning, I might not have gotten to it yet. No, I'm hoping. Well, I'm going to talk about it in a second, so you can sort of decide. And then I will have kind of like the regular tests. I will have the Collaborate Ultra open for basic questions, so you can go into there. And starting at 3, I'll open up a Zoom session. So if you come in before 3, you can ask last-second questions. Otherwise, it's like the other test, which is it really is. If you have a more elaborate question, you'll come and ask the question and go back out. So the setup will be similar to the other 2 tests. In terms of the material, the review in some ways is closer than usual, except for the last question. So again, 4.7, which is question 7 on the review, is not on the test. And that kind of makes it fairly easy to do the test, which is the test will have, in some ways, there are 6 sections on the test, and there will be 6 questions. So there will be one from 3.11, just like number 1. 4.2 I'm going to do in a second. There will be one 4.2, which is what was on the quiz. So question like what was on quiz 4 from 4.2. 4.3 is the conservative. So that is question 3. So there'll be one similar to that, except it could be 3-dimensional instead of 2-dimensional on the review. Then number 2, Green's theorem, which is 4.5. So there'll be one of those. And then, except 4.4, not 4.5. And then 4.5 is, I think, question 4, getting mixed up, which is the base flux. So I give you a parameterization and then ask you to get the flux of a velocity field over that region or that surface. And then a one from 4.6, which is the divergence theorem. And for some reason, I did 2 of those. I think the reason I did was that 5 is the base one, and then 6 is one where you have to do, first you close it to use the divergence theorem, and then you do another part. So instead of one of those, probably one of those, there'll be one instead, like what was on the quiz from 4.2. Also, 6, since I was just making it for review, I didn't worry about, so it's kind of messy, so it's longer than what you'll see on the actual test. Another little thing is on the other tests, I usually didn't have you do many integrals. Here I'll probably have you do more because you'll probably at least a couple times get things like this. And I want to know that you can do them in that case. So let me just remind you, ask you. You can't give me a number, but how would you get that? So what would be, right, so this would be 2 times whatever the area of D is. Since I don't tell you what D is, you obviously can't tell me that, but that says area of D. So because of that, there'll probably be at least a couple of those. I'll probably have you do more integrals than usual, just because they're going to be simple ones where you're not actually doing antiderivatives, or shouldn't at least. So that is test. So first it's general concepts. Any questions about the test? It somewhat depends. So if you're taking it Tuesday, assuming I can consolidate it to get one time, I probably will. If you are taking it at a time by yourself, what I'll probably have you do is just have you email me and then I can set up the Zoom session if there's a question. So it'll depend on when. So I'm going to try to consolidate so that everyone taking it Tuesday is taking it at one specific time, and then I will have a Zoom session for that also. Any other general questions? Okay, so let me look at one specific one type of thing. So the one that wasn't on the review, but was on the quiz is something like, and I'll just make something up. That keep it simple. Okay. I just had to think for a minute to make sure I'm being consistent here. So suppose we have a force field, and I want to find the work to go from the 0.25 to the 0.248 along the parameterization t plus 1, 3t minus 1. So this is a slight variation of what was on the last quiz. So it should mostly be okay. So what are the steps I take? Also, I'll remind you for this one, if I don't ask for the answer, what I would expect you to do. So here, first step, well, whichever you want to do first. Give me one step to do. So you can check if it's conservative, but yeah, actually, so let me make it not conservative. So yeah, check to see if it's conservative, because that's true. Then you just take the antiderivative and plug in the two endpoints. So now it's not conservative. Okay, so it's not conservative. As you said, you really should be checking that, because if it is, that's the easiest method. And then once you see it's not conservative, so qx minus py is not 0, it is y. And what do you do? Right, so whichever order you want to do it, we need to take the derivative of the parameterization. And we also need to plug the parameterization in the force field. That's a 3t minus 1. Those are all parentheses, not absolute values. And then what do I do? And then there's a slight variation, to the integral of dot products. And this is the slight variation, which is instead of having you get the equation of the line, I give it to you. So in one sense, that's easier. But since it's backwards, there is this slight difference, which is if you use the equation, you're always going to go from t equals 0 to t equals 1. Here, you have to figure out what it is. So here, what are the limits for t? Right. And how it goes? Not very difficult, but if you haven't seen it, it's not necessarily immediate. Right, so set the two things equal. So for the first point, I want to find for what value of t is t plus 1, 3t minus 1 equal to 2, 5. So just set t plus 1 equals 2. For the second one, plus set t plus 1 equal to 4. And so that gives us the 1 and the 3. And then for the test, if I just said for you to set up, kind of like the quiz, I would expect you to do all the preliminary work. But once you've done that, so that includes the dot product in this case, you do not have to simplify and you do not have to take the antiderivative. So we have that this is equal to this. So I'm going to use the first component. Which tells me that t plus 1 is equal to 2. So there's the t equals 1. And if I do the second component, I get t plus 1 is equal to 4. Okay. So as I said, it's not difficult. It's just, if you haven't seen it before, you have to think about it. No, because well, the only reason you might have to is to make sure it has up. So we need both to be true, obviously. We also need 3t minus 1 is equal to 5. But that should, or better, also give the same value. And it doesn't. So what should it be if this is going to be consistent? Wow, I did that very well. What should that be for this to work? So yeah, so thank you. So the only reason you have to is double checking to make sure I haven't done something stupid like I did here, that it's consistent, but it better be, otherwise you can't do the problem. And that means you have to be consistent. If you have two and one is more complicated than the other, so for example, suppose the parameterization was something like t 3t squared plus 5t minus 7, then obviously you're going to use the first component to figure out what t works. Or if it's a reverse 1, you'd use the second component to see what t works. So since both have to be true, you can choose your 1. So this would be instead of, say, question 5. So a question like this, either one where you have to get the parameterization, like on quiz 4, or one where I give you a parameterization, like here, where you might have to then figure out what t's work. So other than that, as I said, it's pretty much like the review. So 4.2, 4.3, 4.4, 4.5, 4.6, pretty much one question from each. And since you have those, let me just ask, any one type that you want to go over? Some, at least, I can make up variations pretty easily. So 4. The last two, okay. All right. So 5 is pretty easy to make it, although it might not be a nice one. So this one is I'm going to make it fairly simple so that it isn't too bad. So here we want to find, and I'm being lazy here, so hopefully I can fit everything in. So given this vector field, we want to find the flux over the surface parametrized by this. So this is the 4.5 question. So we'll see if I can fit everything. So what are the steps for this? Right, so get the partial derivatives. So RU RV. And then there's a variation of this, which I usually put into the divergence one. So take the cross product. Okay, so like that. And then so we take cross product, and then we do the parameterization into the vector thing. So I get that's supposed to be an x squared, so here I've again done a slight variation, which I've used in I forget which problem, but oh, I know, the surface area one. So then the last step is to, so I have the cross product, I have the velocity field with the parameterization plugged in, and then I take the dot product. In this case, the way I've given you the limits, does it matter which order I do? Or asked in a more specific way, which order should I do the integral? Right. I don't have to. Oops. But because the way I've done it, you would have to draw to rewrite parameters if you wanted to do it du dv. So it's written in that form. And then here, just like the last one, I would expect you to take the dot product, and if I just asked you to set up, ask you to get the dot product, which is the 4u squared v minus 2uv minus 2uv. And then you could stop if I just asked you to set up. So again, all the preliminary work, actually I'm also doing this since that's easy. I asked you to set up, you would go as far as that. Again, I'm specifically not simplifying, but of course you can. So that's one type, 4.5. And then there's an easier one, which I'll do in a second. But any questions on this? Okay. This one we've done more in the context of the next section, but let me do one by itself. So again, vector field. Just different. So in case you can't read it, because I love writing. So the vector field is just really simple. It's x, y, and z squared. And we want to find the flux on the surface M, which is a square at x equals 2, where y and z are both between 0 and 4. So this is a much shorter one because we don't have to parameterize, although this would be a pretty easy parameterization. It would just be 2 comma u comma v. But the reason we don't is it is flat, which means the normal vector is just a constant. Here, what is the normal vector? And that's because we have something that's parallel to the YZ plane, so it's pointing in the X direction. And therefore, when we get this, we don't have to put in the parameterization, but we do put in what we know. So what is that first vector? Right. In some ways, it's 2 comma y comma z squared, but we don't care because we know we're taking the dot product with 1, 0, 0. Which means we know that we're going to get just that first term. So in this case, the 2. And so this is what I started in the first slide. Now this, you don't actually have to do the integral. So in this case, it's 2 times, just again, the area, which in this case, since the square is just a 4 squared. So this is the second type from 4.5, one where we're still doing the dot product of b and the n. It's just that we can do it in a more basic way because the surface we're looking at is flat. So we can just read off the normal. In theory, I can make it at an angle. So for example, if I set a square in the plane y equals z, in which case you'd have to figure out what it is, but we haven't done enough. So if I'm going to make it flat, it'll be parallel to one of the coordinate axes. So it started out as 2, but then I didn't want it to be the same as the x equals 2. So both y and z are from 0 to 4. We get 32. Okay. So any other questions on this? Right. So if it had been 0 to 2, I would have been a little bit weird calling it a square. but yes. Okay, anything else? Okay. So the 4.6 is the divergence theorem. And why not? There aren't too many nice examples that we can do here. We do things like cones and spheres and cylinders and I'm trying to think what else. Paraboloids. So not too many things actually. So I do a paraboloid, which I think is one we did. I forget. Give me a second. I'm going to look at the review to make sure I'm not doing exactly the same thing. It's doing a paraboloid there. This one was cylinder. Okay. So let's do v is equal to what? So let's do this vector field, and we have the cone, which is, if we're looking at it this way, actually I might be able to draw it. Cone's pretty easy. Pointing this way and closed. Then let's find the flux through that surface and orient it out. Again, the only difference if it was oriented in is after you set up the integral, you just put a negative in front of it. Okay, so for this one, obviously we're going to use that divergence theorem. What does the divergence theorem say? It says the integral of the v dot n is s is equal to what? The triple integral, I'm going to call it E, but you'll tell me in a second what that is. Actually, I might just do it since it's... So in this case, what is E? So M is the surface, the cone plus that end. What is E? It's the solid, so it's a three-dimensional thing, whereas M is just the boundary, so not including the space in the middle. It's just the outside of the cone together with that one surface. Okay, so for the divergence theorem to work, we need it to be closed. What is the divergence? Either here specifically or in general. So what is it here? Yep. Because it is the derivative of the first. So derivative of p with respect to x plus the derivative of q with respect to y plus the derivative of r with respect to z. And we get this. All right. So I'm going to do this two ways, because one way is, since that's a constant, it's just going to be the volume. But do you know offhand what the volume of a cylinder, cone is? I think I do. Something like 1/3 height times pi r squared or something like that. So if you know it, you can just use it. If you don't, let's actually set this up. So let's pretend you don't remember the formula for the volume of a cylinder, which if this is a paraboloid, there is a formula, but I'm sure you don't know it. So let's set this up as if we don't know the volume of a cone. That's why I keep saying cylinder. So I'll do it in two steps as I usually do. So the inside one, so it's going to be the 7. I'm going to do dy first. And that's because, in that case, what are the lower and upper limits? Oh, oops. This actually isn't a cone. This actually is a paraboloid. I forgot the square root. So this actually is a paraboloid. So I say cone, but paraboloid. So I really don't know the volume. So y goes from, so remember we're looking for what function do we hit on the left, which is the paraboloid. And what function do we hit on the right, which is, I lost it, y equals 3. And so then we want to project into the xz plane, which is of radius 3. Oh, that's okay. What happens when I make up things? So what coordinate system do we probably want to use? Right, polar. So this would become, the inside will become r squared to 3. We'll get the usual r. R goes from 0 to the radius, and theta goes from 0 to 2 pi, as usual. So this is if it's closed. If I had the same space, but instead of being closed at y equals 3, we just take the cone until y equals 3. Not the cone, the parabola until y equals 3. Then what can we do to use the divergence theorem? So I should actually put in divergence theorem. Square root of 3. I wasn't thinking. It was going to be a cone, which would have been the square root, so the radius would have been 3, but then I made it into a paraboloid somehow. So it's square root. So 0 to square root of 3, and then the outside is the usual 0 to 2 pi. So suppose I get rid of this, but I still have it just go until 3. Then how could I use the divergence theorem? And what extra would I have to do? Right, so I could put in the disk, do this same integral. It's just that this wouldn't be the final answer. I'd also separately have to do a flow through the disk, which is similar to the one we did just before, a couple slides ago, and then subtract it off. So add the disk at 3, get the same integral that we just did, get the flow on the disk at 3, which is just the x squared plus c squared is equal to 3. Read off that the normal here, and let's see if this works out nicely. What is the normal here? No, I didn't make it nice. So I wouldn't do that in this case, but what would be the normal at the disk? 0, 1, 0. And you can see that's not going to be quite as nice because I'm putting in y equals 3, but then I still have the variables x and z. So it would be a bit messy. So any questions on this? So that is 4.6. So pretty much there aren't too many that we can do, any types of surfaces that we use in 4.6, because we want it to be something that projects nicely. So paraboloids do, cones do, spheres do, obviously cubes do. And I guess pyramid type things would also, but there aren't too many. All right, so any other questions on this? Okay, any other types that you have questions on? So the only types that we can read off are ones where it is flat. So in this problem, if we were doing it the direct way, we would have to parameterize because since it's a paraboloid, the normal changes depending on where I am. So we'd have to parameterize, take the partial derivatives, take the cross product to get the general normal. But the disk at 3 is parallel to the xz plane. And therefore, the normal would be pointing in the y direction. Pretty much the only ones I do are ones that are pointing in the x direction, which would be 1, 0, 0, pointing in the y direction, 0, 1, 0, pointing in the z direction, 0, 0, 1, or the opposite one. So if I did it where I put this on the opposite side, or if I said we're oriented in, then we could also get the 0, negative 1, 0. So if it's parallel to the xy plane, then you're getting along the z-axis, which is 0, 1. If it's parallel to the xz plane, then you're going towards the y-axis, so 0, 1, 0. And if it's the yz plane, you're pointing in the x direction, and you get 0, 0, 1. So pretty much you can just remember those are the 3 types, just with the possibility of a negative. Okay. Any other questions? Either this or other sections? So this one, since it's a little bit longer, if this was the actual question, I would probably just have you set up. Because obviously this isn't a difficult integral, but I would want to save a little time. As I said, there'll probably be a few more questions where I ask you to actually get the value of the integral. Right, so the idea is if I ask you to just set up, that means you have to do all the preliminaries, which in this case means take the divergence and then set up the limits, but then you don't have to do anything more. And on the previous one, if there's a dot product, you have to take dot product. So if I say set up, get it to the point where you have something like this, but you don't have to simplify, do the algebra to simplify or do the antiderivatives, right? So this, if I just ask you to set up, how far you'd have to go. right, so people, actually no, someone just joined. Pretty much that's what it is. So it is, if you look at the review, it's about the same as 1 to 6, except with two things different. One is instead of 5, there'll be one similar to the one on the quiz from 4.2. And then the question like 6 would be shorter if there's one like that. So about like 1 to 6, roughly, on the review. All right, so as usual, let me do this, which is let me stop recording. But of course, if you're ready, we're done.